Uh, Good morning, everyone. My name is Mustafa Shaqawi. Uh, this work was done with collaboration of Dr. Ti Hui from Singapore University of Technology and Design and Dr. Ichim Wei from Chengong University, Taiwan. So today I'm going to present our work under the title of FPGA implementation of tiny transformer using high-level synthesis for biomedical application. So basically, I will speak about the problem context, the aim of this research, introduction about the tiny transformer model, um, speak about the approach we talk regarding the high-level synthesis, and implementation, and then speak about the results, discuss the results and reflect on them, and then conclude with the summary and the future work. Um, so uh, basically, in order to detect the abnormal heartbeat or what's known as cardiac arrhythmia, we have two options. First is to take the electrocardiogram signals, send them to some cloud, process them, and then get the results. And this, of course, involves some limitations regarding the latency, regarding the internet connections, regarding the privacy. Or we could go for the edge computing, which is should be faster, preserve the privacy, uh, and this needs to be continuous, and this needs to be continuous be done for efficient monitoring. Uh, so we choose the transformer model basically because since it presents the state-of-the-art performance for sequence data, uh, especially in capturing the global context, something very important in determining the global rhythm in ECG data. Um, uh, but the challenge here is that the memory and computational requirements make them not easy to deploy them on the embedded systems with a tiny power constrained hardware. So prior work have introduced a lightweight transformer. Specifically, we are speaking about a paper that introduced a tiny transformer model for ECG arrhythmia classification. So this work that we are presenting today aims to move beyond the microcontrollers and explore the FPGA deployment. So our research aim is to basically deploy this tiny transformer model, introduce a functional correct implementation with acceptable resource utilization that doesn't violate available resources. So this is a tiny transformer model. It consists of three stages. First is the embedding stage. It's simply CNN that takes the ECG data, 198 points, sequence data, try to do the patch embedding, which is learned through training, and then go through the normal transformer sequence for encoder. At the same time, we also concatenate, we use a dense layer for concatenating some critical information about the heartbeat itself, which is the distance between the two heartbeats, including the pre-RR and post-RR distance. And all of this is concatenated through a dense, finite dense layer that classify the type of the heartbeat into one of the five classes. So the good thing about this model is that it compromises only a few number of parameters, around 6.6K parameters, and it could be trained for any sequence function. In this model, it was trained to classify the ETG arrhythmia. So first thing we do is we replicated the work. We took the MIT PIH dataset, which is around 120,000 heartbeat, containing 48 and a half ETG recording. We did a pre-processing. Since they are continuous data, first we need to segment the beats and then extract the RR interval, calculate the pre-RR and post-RR, and then normalize it to some threshold, make it easy to train the model. Then we split the data, 70 train, 10 validation, 20 test. We took a batch size of 128, learning rate 2 multiplied to the power -3. We trained this model on the Google Colab environment. Then we could reach very similar results to the reference paper of 98.91% of validation and testing of around 98.83. So second step was to go through. We need to implement this model on the deployed on the FPGA. So first we have two options: is to go through the RTL implementation, which could take some time due to the complexity of the transformer model, or which is we talk the high-level synthesis approach. The high-level synthesis approach, basically we implement our model using C++ language. We do the C simulation first to make sure that the functionality is correct. Then we try to synthesize the C code into RTL code. Then we do the C RTL code simulation to make sure that our software implementation matches the generated hardware. Then at this point, it could be ready to be exported as an Vivada IP, which to be implemented on the specified port. In this work, we choose the KV260 port, and approach is the HLS approach that I already clarified. So basically, first we model components. We implemented it on C++. We take first, since I mentioned that we take the Python model to take the weights and prices of the Python model, and then we fed them into the C code as a vector, as a matrices, as the tensors for the implementation. Then we did the simulation on multiple heartbeats, and then the results came consistent with the Python simulation. Secondly, is that we tried just a basic synthesis that meet the timing requirements, which are different timing. We started with 8 nanosecond, then we go to 10 nanosecond until 15 nanosecond with timing that met the timing constraint. We then did the C synthesis, and the model RTL was generated. This RTL was then mapped to the FPGA resources, and the utilization I'm going to show on the results section. Thirdly was to make sure that this RTL matched the C simulation, which is have been already passed the C simulation, the co-simulation. So the results came that the implementation achieved 56.62 millisecond inference latency at 76.9 megahertz operating frequency, with utilization ranging from 20% for flip-flops, maximizing to 30%, 37% for the VRAM. So results have shown that the feed-forward network had the largest computational component in this base model, consuming almost 55% of the total inference time, followed by the multi-head attention block, around 40%. let's see that we have a chance to do some kind of architectural changes, including also the parallel processing of the 8 attention heads, and at least to that we need to also optimize the feed-forward network since it's taken most of the time. So basically, in this work, we introduced a simple functional uh, FPGA implementation of the tiny transformer. Uh, and the next step that we are taking is to try to parallelize this the attention the attention processing, the attention calculation processing as it can meet the port resources, and try to accelerate the performance using some strategies like pipelining and memory partitioning. Yeah, so this was our work. Yeah, thank you for listening.